Cool. Jonathan, can you see the board?
Yeah, I can see it.
Cool. Awesome. All right. Today we'll talk about solving problems with hash tables, and we'll see how they are so handy for a wide array of problems, especially when you want to optimize your algorithms, your runtime. Some pros about some other names that you might find out there are hash table or object or hash map. Hash table, object, map, dictionary, or dictionary in particular, for example, is heavily used. That language is heavily used in Python, where everything that's a hash table or an object, that we would call that, Python calls a dictionary, etc. Well, the main pro for hash tables are that they provide constant time lookup by key. You can get an element from a hash table in constant time if you have the key that is storing whatever you're looking for, and that turns out to be quite handy again at handling and implementing optimizing algorithms. Some of the cons from hash tables, which actually could be seen as pros as well, are that a hash table does not allow to have duplicates. For example, you cannot have two keys with the same. You can't have two keys that are the same, for example. Hash tables are on order, so that means you cannot rely on the order of the data being stored. If you have numbers, for example, you don't know how those numbers are going to be stored. Maybe descending order, maybe ascending order, etc. You cannot sort the keys on an object, for example. They could be inefficient in the use of space. This goes back to the session where we talked about the hash table implementation, where we saw, actually, I think I have something about that here. The hash table is actually an array under the hood. This was on our last session that we were looking at the hash tables, and that's just sort of to recapitulate here rather briefly. A hash table is basically is an array under the hood where you just basically take a key, you hash that, you pass that key through a hashing function, and the hashing function gives you an index or a hash, and we use that index to key into our array, basically. Then for this example here, oops, I think there's someone else joining. Let's see who that is. Join. Great. So as we see here, for example, I think actually, and let me try to write here. We say, oh, give me 1 sec. I move my pen to be looking at my second screen. Cool. We can say that the key Maria, for example, we pass that through our hashing function, and we get back, actually, let me just copy this. We get back, let's say this is an example, this is, we will get 10. And we saw that hashing function could be as simple as adding all the character codes from the single characters of the key, Maria, and that modulo, how many elements, how many slots we have in our array, underlying array, can give us the hash. In this case, yes, an index. So we will say what we'll do is if we hash Maria, and let's say we basically want to have a mapping of usernames of like Maria to their email. We want to somehow map. We want Maria to be the key and her email to be the value. Let's say Maria 123 at maybe gmail.com. Right. If that's the case, let's remove this here. Then we hash, in this hypothetical scenario, we hash Maria. We say the hash function returns to us 10. So that means that this email will be placed at index 10 of our array, which could be here. And in fact, it's actually two things get stored. The key gets stored, and also the value gets stored, but also the key into essentially a node that has, yeah, maybe I could just do, oh no. A node that can have a key and value. This node for Maria will have the key and we'll have the key and we'll have her email. So this gets created, I know it gets created with her key and a value, and then this node is basically being stored here at index 10 of our array. Right, and let's say we want to store Joanne. We pass through Joanne through our hashing function. The key is Joanne, and the value is her email. That could map out to maybe index 17 and so on. It depends on our hashing function. When there are collisions, what happens is, let's say in this case with Douglas, we pass Douglas as the key through our hashing function, and it returned 29. So Douglas was the first node to be put there. And let's say that for some reason, Siham, the key Siham, also mapped to the same. We hashed that, and we ended up with the same index, or Siham ended up being mapped to 29 as well. In that case, we use a linked list on the array to chain multiple nodes together. So this is a way in which you can solve for collisions. When two keys end up having the same key, the same hash, then we can just chain them together. For example, let's say if Alejo for some reason also mapped to that. In that case, to insert Alejo, we need to check if there is a node already there. If there is, we go to the next. If the next is not available, if there's something already there, we just go to the next until we find the next that is available. And we put, in this case, Alejo with the key and the value, which will be something that looks like this. There, cool. So based on that, basically under the hood, a hash table could be a bit inefficient in terms of space, because there is, imagine this is an array of 30 elements, and there's basically 1, 2, 3, 4 elements being occupied, and for elements being occupied, that means 26 empty slots that are still reserved for the hash table, but are not being used. So that can be seen as a down or a con on the hash table. However, though, this is outweighed, this con is outweighed by the constant time lookup. Constant time lookup is really wonderful and basically outshines all the cons from this. Then, the fact that it doesn't allow duplicate skills could be seen as an advantage. But let me stop here. Any questions or thoughts on sort of the pros and cons of hash tables or objects? Okay, thank you, John, for the feedback. Okay, so when can anyone just say what are some scenarios you think or that come to mind when it will be helpful to have a hash table? Anyone, just unmute yourself and shout it out.
Looking up items in the shopping inventory.
One more time.
Let's say that we're looking through our store inventory. We would want to have an object to just like hold let's say like we're looking at oranges and we want to sell them for like 45 cents an orange. We can put it in a hash table.
So what is the value and what is the key and what's the value?
The key could be orange and the value could be 45 cents.
Got it. Cool. So if you want to find the price of any product from your inventory, that will let you know the price of any product in constant time lookup, because you just hash the key, you just hash bananas, and that gives you the index at which bananas will be found, and that will be happening really quick. Oh, hey, George.
Yes, I have a question.
Sure.
So, are you saying like hash tables are basically objects, or?
Yes, they are. Yes.
What's like what makes them different? I guess is it objects you can have duplicates or?
No, so all these are synonyms. Basically, different programming languages call them differently. Hash maps, hash table, object, dictionary, hash map. They're all the same, which is this concept of we have keys and value pairs, basically. And object is just the name that JavaScript gave it. I think Java uses hash map. Python uses dictionary, but they're the same concept, the same idea of key value pair stores, where you take a key, you hash it, out of the hash you get an index that then is a corresponding slot in an underlying array that for the most part we can just forget about.
Okay, thank you for the clarification.
Absolutely. Joanne.
For the hash maps, you could only use them if, let's say, you have an array and the sequence doesn't matter, right? And you just want to keep track of how many times a certain number appears.
Awesome, great. That's an example of when do you want to use a hash table, when you want to kind of keep a tally of how many times you have seen something. That is absolutely correct. And you also brought back this point about hash tables are unordered data structures, so they don't have any order, ascending, descending. You cannot order its keys, etc. And if we think about like why that is if we go back here is, here there is no, for example, in arrays, the order of insertion matters, right? If you push an element, you push A and then you push B and then you push C, then they will be put in order. In at element at index 0 you have A, at index 2 you have B. At index 1 you have B, and at index 2 you have C, right? In arrays is the order of insertion. In hash tables, we hash A, it could be any of its any index. We hash B, it could be any other index. We hash C, it could be any other index, and that's why we cannot rely on the order of the hash tables, because they could be mapped to different indices in the underlying array. And I guess you could say, well, but we could use the underlying array to have an order, and we'll use that. But the thing is, at least in JavaScript, we do not have access to the underlying array. This is sort of like how it works behind the scenes or under the hood for us to have a more in-depth picture of it. But we cannot access that array, at least not in JavaScript. Maybe in programming languages like C, C++, C#, there might be ways, because those are more sort of low-level programming languages. Yeah. Cool. Other questions or thoughts on that? Okay, so yeah, you give me some good examples. Here are some other examples. Like one simple and maybe obvious one is like when you need to retrieve an item quickly, like the example that Jonathan gave us. Let's say we want to know the price of items really quickly. Hash table is the best for that. When you use when you want to check if an item exists already quickly. When you want to create a pairing or a map of values, same example applies. For example, Jonathan's example about products and prices, or this is an example as well. Maybe pairing a mapping or a pairing of maybe this is kind of the opposite of what we're doing in the other one. Let's say we have the email. I want to be able to retrieve the full name of a person really quickly. We could have that pairing, we could have that mapping in a hash table. And if we have the email, we get their full name really quickly. Oops. Should be able to run that. Cool. Oh, I guess I didn't finish this point. When your algorithm is rather inefficient in time complexity, you should think about using an object to see if an object could help speed it up. And similar, the example that Joanne gave us, when you need to tally up results, how many times each number appears in an array, for example. These are all good instances where you can use an object for. Questions or thoughts on this? Okay, I see a thumbs up. Thank you, Jonathan. Okay, cool. So let's see. Okay, let me go to REPL and sort of very quickly we'll do. Oh, maybe I should have called it objects review. So very, very quickly, let's say we have an object. Let's say this is an object called, I know, oops. Oh, I think we have maybe two Joannes. That's interesting. Let's say we have an object called car, right? Now, let's say we want to add a key called make that should hold, let's say Ford. How do we add a make property to an object after it has been created. Mhm.
After it's been created, wouldn't it be car.make equals forward?
Okay, there we go. Thank you. Car.make equal forward. Awesome. So it makes sense to everyone. Cool. Now, maybe so Jonathan, you went, Ohidor or Joanne, how do we get that this car is a, how do we get the FWD property?
You would key into, so you go to car
Mhm.
dot forward.
Oh, so the FWD meaning four-wheel drive, let's say.
Okay.
Four-wheel drive. Okay, yes, this is how we can, I guess we can get the property, and if we console log, if we console log the car here, we should be seeing, we have our make Ford FWD true, and we're able to get this. So what is the time complexity of adding a property to an object?
Linear.
Nope.
Constant.
Constant. So 1, also known as constant. What is the time complexity of getting a property of an object?
Isn't it constant time as well?
Constant time as well. Time constant. Okay. Space complexity, there. Well, space complexity doesn't really count in this, or it's not as important in this scenario. Okay, so we have sort of add, retrieve. Does anybody know how to delete a key from an object?
No, I definitely forgot.
Let's say we wanted to do electric. We wanted to delete the electric property. No ideas, Ohidor, Joanne?
You want to delete the electric property?
Yes. It uses a keyword. So it's actually delete car.electric. This deletes a key from an object.
Oh.
Yeah. This is not like we don't use this quite often, but it's quite handy to know. Okay, the time complexity of this?
Wouldn't that be constant time as well?
Constant time, bingo. Okay, so this is a really cool data structure. Because an array constant time insertion, I guess an array has front and beginning, right? Or front and back. I mean, an object doesn't have a front and a back. You don't really know what's the front of the object, what's the back. Because again, they are on order. So we have insert, like I'm missing one. Insert, what about this? What if we don't know, we want to, I guess, I'm not sure how to put this question. What if we wanted to search all the values of an object to check if there is some match? Let's say, what would be a good example? Let's say year. Let's say 2015. What if we had to search all the keys of the object to see if one of them has the value 2015 in it? How could we do that?
Would you use like a for loop?
That's
So it would
correct.
be like for in
Correct.
car.
So we have to say for let key in car. So it's a for in
Yeah.
loop, which you got correct. And here we could check if car dot key, which is going to bring up the value, is 2015 return true, for example, or console log made in to car key. Right. So basically, sort of searching on an object. What's the time complexity of that?
Isn't that O of n?
O of n, where n is what?
N is the amount of keys that are in the object.
That's correct. Number of properties or keys, those are good. This here we get O of n for searching. If that is, it's a bit of a contrived example, but if we wanted to search all properties of an object for some specific value or some specific key, we will need to loop over the object, and we will need to do this for loop. And this for loop, we don't know which key is going to be visited first. It might be electric first, then year, then make, then FWD. We don't know which key is going to be visited first, because again, hash tables and objects do not have a sense of order. Cool. I think this is pretty much it on this end. Search. Let me see. Basic operations of hash tables. Kind of feel like I'm maybe missing one. Search, insert, delete. That's it. We got them all. And retrieve, I guess. Search operation, insert operation, delete operation. You see, this is, for example, I think this is, what is this in? This looks like Java maybe, or C. No, this is C. Struct. Yeah. Cool. Okay, so we have the basic operations. So we can see that across the board, or most important operations, which is retrieving, inserting, and deleting, are constant time. Searching is linear time, where n is the number of properties in the object. Questions or thoughts about this? Cool. So from here, where do we go from here? From here we go, what is this? Instruments. I didn't open that. Close a few things. Cool. Now let's go to Okay, so now I'm going to show you. So we'll see, before we actually get into the first exercise, we will see an example. So actually, no, we'll do the first exercise right now. So what I want you to do is actually then here, I'm gonna put it here. But I could also, I'm gonna also put it, I'm gonna copy this in the chat. So this is the first exercise we'll start with. I put it in the chat. So the exercise is, I want you to write a function called remove braces that removes all curly brackets, square brackets, and parentheses from a string. And it should return the new string. So also, if this is the first thing that you see a comment like this, this means this is the description of the function. This is what the parameter is. The parameter is going to be called string. Actually, if I show you, in VS Code has a better syntax highlighting. To show you here. We can see that this is a specific kind of comment called JSDoc, which is for documenting functions, and the first lines are usually just a description of the function. Then there is add param, which means what is the param. You can even see that VS Code even highlights it, which is kind of cool. The parameter is going to be a string, and it's called str, and that is a string to remove braces from, and it should return a string without braces. So here are some examples. There is D opening parentheses, ON closing parentheses, K closing curly brackets, opening square bracket, EY closing square bracket, and it should remove all of them, and the word should be there for us. Donkey. If we have, this is some ASCII art that I found online, I should remove all the curly brackets and parentheses. If we have only curly brackets and parentheses, we should get an empty string. So what I want you to do is either on REPL or on VS Code, let's take 5 minutes to implement this. Actually, let's take 7 minutes, and we'll talk from there. Let's take 7 minutes to implement this function. So either on REPL or on VS Code. I'm going to put the timer. And I share the initial code on Slack. Sorry, not on Slack, on Zoom. I think I said 7 minutes. Feel free to ask any questions if they come up. Okay. How did it go? Mhm.
I wasn't sure how to approach the question. So
Okay.
I noticed two ways you could do it.
Mhm.
And one of them was like to have like a if statement of if this contains this character, and
Mhm.
like, you know, if it includes this, then, you know, when you're printing it out, don't include it, like
Okay.
with the exclamation mark. And then the other way was, I remember there was like a JavaScript thing. It was like dot replace.
Yep.
So that
That, yeah.
that one was
Those two ways will work. That replace will use something called a regex, which is something a bit more complicated. But those both will work. Did anyone get to working code? Jonathan or Joanne?
Sorry, I'm still working on it.
Me too. I'm kind of like halfway there.
Okay. How much time do we need?
Maybe 3 minutes.
Cool. Let's do 3 minutes. Also, Hidro, if you want to implement that, yeah, or try to implement what you were saying with the if statements, is fine.
okay.
One moment. Okay. Any working code? You guys there?
No, my code's not working.
Okay. How about yours, Joanne?
I feel like I'm so close, but I need to run it.
Okay. Do you want to share your screen?
I'll share mine.
Okay, cool. It's
There we
taking a
go.
little bit to load for some reason.
There we go. Can you see it now?
No, I still see a black screen.
Leia?
Yep. Can you hear me?
Oh, still? Or you see it now?
Okay. Yeah, I think I can hear you now.
Hey, cool. I got the first brace to leave. Everything else I can't get.
Got it. Okay. Hoidor and Joanne, let's take a look at this. Any I see you had the right idea.
I used the for of loop earlier.
Either or would work. Actually, yeah, either or would work. But anything, yeah, Hoidor or Joanne, you notice?
Mm,
I think he has to do a string at I is not equal to every single thing there. Instead of, I don't think it would work that way.
Okay, so what way do you suggest?
So string at I is not equal to the opening bracket, I think, the first one. And then or, and then you have to do string at I is not equal to the closing one. And then you keep doing that.
So what we need to do is basically a lot of, well, some repetition there where you check if string and I is not equal to the opening parentheses, or string and I not equal to the closing parentheses, or string and I not equal to the opening square bracket, or string and I not equal to the closing square bracket, or string and I not equal to the opening curly bracket, or string and I not equal to the closing curly bracket. Does that make sense?
Yeah, it does. Wasn't
Cool.
there a regex way of doing it where I could have used the
Yeah, with a regex we could do it, but I actually want us to look at this way of doing it.
All right.
So how do we fix this?
I think maybe he could have another variable for string at I guess.
That'll make it a bit shorter. Yes, that'll be good. Yeah,
since the string contains all the braces, you could just put and instead of or.
But if we change these ors to ands, it's still not going to work. We still need to make each comparison one string at I against whatever, or string at I against whatever. Yeah.
Okay.
So let's do maybe as Joanne suggested. Let's create a variable before line 5. Maybe call it char, CHA, that is going to be equal to string at I. Cool. And then we're gonna say then do char not equal opening parentheses only, or char not equal closing parentheses, and so on.
gonna be one really long if statement.
And maybe you want to like just copy and paste the line stuff and copy and paste it. Okay, and remove the parentheses. You have some extra parentheses. You need to remove the parentheses you have on at the end of line 10 to line 7.
Oh, yeah.
Okay.
Still missing it.
Oh. Actually, then I actually think you want if it's equal to one of these, not if it's not equal to one of these, let's copy it.
If it's equal to one of it?
Oh, wait, hold on. Oh, maybe this is what Hidur was mentioning. No, instead using an and, hold on. If it's not one of those,
I think it was an and.
yeah, this thing's, let's see.
Bingo.
Awesome. This kind of things still get my brain to think. Cool. Does this make sense? Thank you, Hidur, and thank you, Jonathan. And also Joanne, because you all built this solution basically collaboratively. Questions or thoughts about this?
The regex probably would have been a hell of a lot easier.
True. Or like shorter, and maybe not easier, but shorter for sure. Yeah.
Can you show like with the includes method?
So with the includes method, let's see.
Because I know with the includes method, you can use it to just like it'll show that it's included, but when you want it to print out, you don't want those to be included.
Yeah, actually that one problem that I'm identifying with the including is that it will tell us whether it is there or whether it is not, but it's not going to tell us.
Yeah, it's a Boolean.
Yeah.
Okay.
Yeah. We need to check every single one individually. Cool. Okay, this is good. So this is cool. So what I'm going to show you now then is how could we this is okay. Maybe we could have also written different if statements. If it's not the opening one, then if it's not the closing one, then if it's not the opening square brackets and so on. We could also have done it instead of combining with the and, have separate if statements. But I guess I remember yesterday, one of these things which I hope to transfer to you now is how we could use an object to save if statements or to reduce the number of if statements, and sometimes to make them even clearer. So that's what we're going to do here. So that solution, I wanted you to look at that because hopefully to see how this could be the same, but maybe a bit more easier to understand, etc. What if we had an object? Let's say we say let braces. And the idea is that so that we can only have we have only one condition in our if statement to check for multiple at once. And that's one of the things that I learned at some point when I was a fellow at Pursuit that I just stuck with me. So instead of having that bunch of ors, we're just gonna do this. If braces, well, we'll do for So let's do for, where's my fingers today? Let's do char of str. If braces char, actually, in fact, we're going to say if not braces that char, we're going to copy that. Well, we need an output. Let's do output plus equal char. What we'll do is, let's do let output here, just an empty string. And then we're only going to have this one conditional. But what we'll do is we're going to have all the set of braces in our object. So we could say, we could do something like opening parentheses, true. It could be any value. The value doesn't matter as much on this one. Closing parentheses, true. And then opening square bracket, closing square bracket, opening curly bracket, closing curly bracket. So we could have it like this, maybe even like this. So we're not saving a lot of like lines of code. It's maybe roughly the same. But then here we could use this object to have all, basically, these are all our true cases. And we could say if the current character is not in the braces object, then let's copy that one over to the output. Otherwise, this don't do anything. Let's try this. Let me comment this out here. Save, open the terminal. See the, I think, node exercises. Oh, we got undefined. Why do we get undefined? We talked about this on Monday, but I think only John was there. Why do we get undefined here?
Because you don't have a return statement.
Bingo. Great. Thank you. Return output. The default return value when you don't have a return statement is undefined. Why is there an apostrophe here? Maybe I typed that. I didn't realize. Yeah, so we have donkey and then the little face and then an empty string that we don't even see. Cool. But questions or thoughts on this? Another way of solving that problem. Okay, I see a thumbs up from Joanne. Thumbs up from Jonathan. Oh, Hedor, questions or thoughts? Okay, thumbs up. So the sort of the pitch in here is that you could use an object to check if certain element is a member of that object quickly. So here we have this object that has all the braces, and we can check. We want to check if the current character is a brace. Basically, this is what we're doing here. If char is not a brace, right? And also, now that we're here, there is. Let me ask this question first, because I think it's something that we might be new. How many? So this is a way in which we could check if there is a key in an object, right? There are some other ways in which you can check if a key is present in an object. Do we know any other ways?
Wouldn't it be bracket notation?
This is already bracket notation. So one way is maybe one is actually, let's see. Now I done has own property char. Let's double check on this one. Yeah, so this is one. You could do if braces has an own property called char, or actually in this case, char is the variable that is holding the character. So it's going to be at some point D, at some point opening parenthesis, char is at some point D, and at some other point opening parenthesis. And then here we're checking, let's say we're in the parenthesis, we're checking does braces has its own property called opening parenthesis, and we go and it does have its own property of opening parenthesis. Therefore, this returns true, and we negate that. So we're saying if it doesn't have a property with the value that char is holding, let's add it. So this is one way. Braces has own property to check if an object has a key. This is, we could also do this one. This one is reads a bit better. If char, actually we have to do parenthesis, char in braces. If char in braces is easier to read, we still get the same result. Here we're checking if whatever value char is holding, we check if that is a key in our braces object. Is this the first time you guys see this?
Yeah.
Okay, yes, from Julian.
I never seen the has own property.
Got it. Okay, now you can add that one to your toolkit. Jonathan.
I've seen it once before, but like very, very, very long ago.
Cool. Yeah, this is a pretty handy way of checking if an object has a key. In fact, I guess I should say you should try to use this or has own property instead of what we had before. Well, I guess like we just have to be mindful of one scenario. For example, if we do, we had braces, if not braces at char, right? We have this. This works. This works, but this is actually saying if this is actually not saying if we have a char, if we have this key in the object braces. This is saying, do we have this key in the objects braces, and is the value that is holding truthy? Because what happens if the value is false? Let's turn this to 0 or false. Then we're going to get a different result here. We get that one was not removed, because again, this is not checking if the opening parenthesis is in the object. Is merely checking. We basically have a character is the opening parenthesis, and we go braces at opening parenthesis. What is that? That is 0. So 0 or sort of not 0 will be true, which will then get us that character copied. So one thing to watch out for here is if you're doing this notation, you have to make sure that your keys are truthy values. Because if they're falsy, the key might be there, but because this is actually getting the value and evaluating the value and checking if that's a truthy or a falsy, we might get sometimes this issue. Whereas, in fact, we could leave that 0. Oh, I hope this worked. I didn't try this before coming in, but if we do char in braces, oh, well, I guess that's what we had. Oh, no. If we had char in braces, I know that I had to wrap all that because this is what I have highlighted is gonna return true or false, and then I need to negate that. I need to negate that entire thing. And if I do this, see now it still works because char in braces checks for the key directly, and same as has own property, it will check for the key. The value doesn't matter. So just be mindful that when you do this to check if something is in an object, you are usually checking if the value that key is holding is truthy. Does that make sense?
Yeah, that makes sense.
Great. Cool. All right, I see also a thumbs up. Great. Let's go on our next. Actually, let's go on to an example. Okay. Oh, this was the remove braces. So I want you to look at this function, and let's do 3 minutes to look at the function and try to tell me what is this function doing. Actually, give me a thumbs up or a yes once you feel like you have something. Once you feel like you know what this function is doing. Okay, I see a thumbs up, 2 thumbs up. Okay, 3 thumbs up. Cool. Who wants to tell me what this function does? Or I guess tell us, not just me.
It's making sure that we have unique values in the array. So we're returning an array with just unique values.
So what would the output be for this one? Sorry.
So it would be 1, 2, 4, and 3.
Okay. Awesome. Is that true for Ohidoro or Jonathan? That makes sense to you guys? Thumbs up from Jonathan. Cool. We, in this case, we will get 1, 2, 3, and 4. What would we get on this one, Jonathan?
An empty array?
Nope. It's removing duplicates. So what do we get?
66.
666. That's right. What about this one?
All the numbers in the array.
All the numbers in the array. Great. Does the time complexity of this make sense? O of n square nested loops and O of x for space complexity, where x is the number of unique elements. The best case is only one element, which is this. When we have only one element, we only additional space, we're only using one slot. When this is the worst case, when there is no repeated elements, the additional space is the same as the input. So if we got 4 elements in, we're gonna get 4 elements out. In here, this algorithm, or our algorithm, is using more space for this input than for this input, even though this one has even more elements. So for the space complexity of this algorithm, well, actually, let me ask this. What in this algorithm is growing so as to be occupying more space?
Could you repeat that?
Yeah. What in this algorithm is growing that is making it occupy more space? Or that's occupying space as we go along?
Is it the empty array, the output?
That's correct. We're filling in this output. You can see that here. We're filling in the output. So that means that we're gonna use additional space. And as I said, this is the best case scenario for space complexity. If all the elements are the same, it doesn't matter if we have, it doesn't matter if we have 5 elements here, or actually we have 6, we get 1 element back. Even if we had 1,000,000 elements and they're all the same, we're gonna get 1 element back. So this is the best case for space complexity. The worst case for space complexity is this, where we have all unique elements. So this will be linear space complexity. So I guess in the worst case, this algorithm in space complexity could be O of n, meaning if you have an array of 4 elements and all of them are unique, at the end, you're gonna end up with an array, with a new output array that is 4 elements as well. And if you have an array of 1,000,000 elements and all of them are unique, the output will be another array with 1,000,000 elements where all of them will be unique. So we will say that the space complexity in the worst case is O of n, where n is the length of the array. And that worst case is when all the elements are unique, right? More generally, we could say, well, maybe that's not like a very common case. So we could just say O of x, and we could use an additional variable. It doesn't really matter what you pick. But to be a bit more precise, you could say where x is the number of unique elements. And we sort of talk about the worst and the best case. Questions or thoughts about this? Okay, cool, thank you. Now let's take a look at this. What is this function doing?
Sorting it from least to greatest.
Okay, that's the first step, yes. But as a whole.
Yeah, view pull request.
So once it sorts it, it pushes it to a new array.
Okay, but as a whole, what is the output going to be here or here?
Isn't it going to be 1, 2, 3, and 4?
For this one, let's see. 1, 2, no,
Oh,
3, and 4. That is correct. Yes. So this array is being sorted. That is correct. But how did we get there? Tell me more about how you got there. So once this array gets sorted, it gets to 1, 2, 2, 2 from here. This 2 goes away. 3 comes here, 4 there, and then this one here. So once the array is sorted, we end up with this. What is this for loop doing?
It's looping through the array and then pushing the duplicates to another array, or only getting the unique values.
Mm-hmm.
And
That's
the
correct.
unique values are going to a new array.
That's correct. And the way in which it's doing that is it's just checking if these 2 elements are the same, right here. If these 2 elements are the same, if they're not the same, let's push them. In this case, these 2 are the same, so nothing gets pushed on the first instance. Then we move on to check to the second 2. In this case, if they're not the same, we push array at I. Array at I there's 1. So we push 1. Then we move on. We check these 2 elements. If these 2 elements are not the same, we push. They are the same in this case, so we don't push anything. We check these 2 numbers. If they're not the same, we push. Are the same, we check these 2. If they're not the same, we push. We don't push because they are the same. We get to this point. We check if these 2 numbers are the same are different. In that case, they are. We do push array at I, which will be 2, and so on and so forth. We get to this point, we push 4. Sorry, we push 3. At this point, we're actually getting to this compare 4 and undefine and see if they're the same. They are not. We push 4. So this algorithm does the same thing than the previous one we saw, right? Now the time complexity is n log of n, because sorting is O of log of n, O n log n, and in big O notation, we worry about the greatest piece of work. So here sorting is the greatest piece of work, even though we have a for loop after the logging, sorry, after the sorting. The for loop is just linear. It's only O of n, but we pick the biggest. That's why actually where big O comes from. We pick the biggest order, whatever takes the most work, and we use that. So the time complexity of this, we could say is n log n plus O of n. That's really the work. But then log of where plus, wait, hold on, let me see if I say that correctly. The time complexity of this is n log n plus n, but n compared to n log n is minuscule. So we discard it. And we just say n log n. The space complexity is the same as the other one, where x is the number of unique elements. Cool. Oh, one side effect of this is that it sorts or modifies or rearranges the original array, which is something that you may or may not want. At this point, our array is sorted, and it will be like that after the algorithm finishes. Our original array will be sorted, which again, sometimes you don't want to modify the original input. Okay, so we saw these two ways. Time complexity of the first approach with a nested loop that includes a nested loop. N log n space O of x. The sorting method, n log n, where because of sorting in time complexity and space complexity are the same. Now, is there a way in which we could optimize this to reduce our time complexity to linear without sorting, without nested loops, using an object? Thoughts or ideas on that?
Aleo, can you repeat the question?
Sure. So we saw that these algorithms are quadratic and n logarithmic, right? Which are not great time complexities. We want to optimize this algorithm using a hash table to bring it down to linear, which is a fair runtime complexity for this. Could we do that with an object, and if so, how? Any initial ideas?
Couldn't we loop through the array and push the value as a key?
Okay.
So if we in the case of 1 2 2 2 2 4 2 3 1, right? We would loop through the array and see if the key is in there. If the key is not in there, then we set the index of 0, which is 1, as the key, and set the value to 1. And then for every time that we come across a 1, we just increase its value.
Does that make sense to Joanne or Hidor? Cool. Yeah, so that's exactly what we're doing here. Now let's take a look at this.
True works well.
Questions, thoughts? Yeah.
For this one, we loop through the array,
Mhm.
and we store the value of the array at the index I into a variable called num,
Correct.
and we use num as a key, and we say that
Correct.
the key is not in the object.
Mhm.
If the key is not in the object, we push the number. Else, if the key is not in the object, we push the num, and then we put seen where the number is the key, and we set it to true. And the only way that we would see if the object is, well, we have to check the object again at num, which would be the key. And if the key is in there, we will that condition will never run.
Right. We just move on to the next one. Mhm. Oh, hey there, Joanne. Any thoughts or questions?
Not really.
Or does this make sense?
Yeah.
Cool. Yeah, and Jonathan, yeah, we could have counted as well, but in this case, we're not going to do anything with the counts. So we can just set it to true. In fact, now I guess now that we're here, you guys, this is also a good use case for a set. Actually, does anyone want to try to, how do we rewrite this with a set instead of an object? A set will be a bit, I guess, a bit more elegant just because it's easier to read as well.
I haven't used sets too much, but I think I can try.
Sure. And I guess like a set, a set is different from a hash table. It's similar but similar. It's different in the fact that a set only has values. It does not have keys or key value pairs. It's just values, but the set guarantees to you that the values will be unique. You cannot, if you try to add a duplicate value, the set will just not complain, not tell you anything, but that duplicate will never get added. So go ahead, Jonathan.
Can we put let seen equals new set?
There we go. Cool. Now, how do we check if the num is in the set?
If
Those the kids know, right?
array at I, no, if set dot has.
Okay, but our set is in scene, right?
If
So we
has.
Okay, has num. That's it. Oh, actually, no, we do have to do this. How do we add the element to the set?
Scene dot set or scene dot add, right? Yeah,
Add. Yes, and then we will just add the number to the set. Scene add number. In fact, let's run it to verify that it is indeed the same. Well, I guess we didn't run on the first one, but there we go. Oh, wait, actually, hold on. Still running the exercises.
So what is has and add? Are those like push and pop or with arrays? And
basically, yeah, this is with a hash, with a set, sorry.
Okay.
Yeah. Yeah, we got the right ones. I think I just have some other console logs somewhere else. Yeah, this one's, let me comment this one's out. Oh wait, hold on. We're getting empty arrays. Oh, sorry, I meant to say if it's not in the in the set, let's add it. Now we're getting correct answers. Cool. So yeah, has is how you check if an element is in a set, and add is how you add an element to the set. And this is how we create it. Questions or thoughts? And the set under the hood is still doing the hashing, still an array under the hood. All of that is just that it's not a key value pairs. It's not a key value pair store. So in other words, you could also think whenever you don't care about the key, having a key, you can probably use a set for that. But they're similar in the sense that, well, they let you check if something is in there in constant time. They'll let you add something in constant time. So they're more similar than different, really. Yeah, the only difference is that the set has only values, object has key value pairs. So a set is good for, an object is good for mapping one value to another one. But a set cannot do mapping, for example, because you only have one property and one value. You don't have keys, basically. Cool. Other questions or thoughts on this? Thumbs up. Cool. Okay, so then this is much more efficient because we only have one loop. We don't have to sort. So that means this is linear. We know that this line, as we were talking about big notation session, this line is constant time. This line is constant time. This is constant time. This is constant time. So everything inside is constant time. Therefore, we're gonna perform constant time operations n times, where n is the length of the array, right? So this is O of n in time complexity, which is much better. And space complexity, we actually have the same because we do have a set or a hash table. Actually, let's go back to this one because I don't want to get confused about sets over hash tables. The point of this is hash tables. So even though we do have a cin and we do have an output, these are two data structures that are going to grow as we go evaluating our input in the algorithm. Cin will have, let's do it with this example. Let me bring this back. In this example, how many elements are we going to have in cin? How many keys are we going to have in cin here? Come on, guys. We said that we had done already that calculation a few minutes ago.
4.
4. That's right. In this case, 4 as well. In this case, only 1. And that is going to be, we end up with, for this scenario, we end up with 4 keys. So that's the number of unique elements. And actually, I'm not sure if this is where X is the number of unique elements. Maybe instead of unique elements, this should be where X is the number of, where X is the number. I feel like this is, I think you get the idea and we have the right idea, but I'm not sure if I would describe this number of unique occurrences where X is one instance of every number. Maybe another way in which I could put it. One instance of every number. Yeah. But unique numbers also kind of works for this. So yeah, we end up with unique keys here. The output ends up with that same amount of elements inside. So this is n. This is, well, I guess in the worst case, this will be n, which is, this is the worst case. where all the elements are unique, we end up with that many elements in C, and we end up also with that many elements in output. So this will be, in the worst case, is O of n space complexity. We could say on average is going to be O of x, where x is the number of unique of one instance of every number. And then this loop is no, so that's in space complexity. So this is in the worst case, remembering that space and time complexity is often all about just the worst case. This is n. In this case, this particular case, when all the elements are unique, scene will have that many elements. So that will be n, where n is the length of the array. Output will be n, where n is the length of the array. So this is basically n plus n. And then there is nothing else that's growing. So this will be like, we could say 2n, but we drop the constant 2, and we just say n in space complexity. Or if we want to be a bit more precise, we could say O of x, where x is the number of unique elements of all elements at least once. Does that make sense? So space complexity is the same. Time complexity much improved from quadratic to linear. Questions or thoughts? Cool. Thumbs up and then no. No for questions. Thumbs up is no questions. Great. Okay. Let me see. I think I have another exercise here. What is the time complexity of this? Let's take a look at this algorithm. Actually, first of all, what does this algorithm do? Actually, I'm just going to copy it. I'm going to copy it here. And I want you to optimize it using an object. But for that, you need to figure out what the algorithm is doing first. I'm going to share it in the chat here. So figure out what that algorithm is doing and optimize it using an object. Let's do 7 minutes for that. Give me a thumbs up or a yes once you're done.
Got it.
Okay, I see a thumbs up. Cool. Thank you for coming, John. Cool. Haidar, how did it go for you?
It didn't go too well.
Okay. So I think Jonathan, you got doing some work in code, right?
Yeah, I did.
Cool. So let's do this. Arthur, can you share your screen? So maybe with Jonathan's help, we can get you there. Cool.
No, I mean, like I didn't attempt it.
Okay. Wait, no, you did. Isn't this that?
No, this is Jonathan's screen.
Oh, I thought this was a Haidar screen.
Oh.
Okay, cool. Jonathan, walk us through. I guess what does the algorithm does first of all?
It's checking to see if the array has duplicates.
And if so?
Return true, and if it doesn't, return false.
Okay, cool. How does it do that then?
I would have to. Well, I'll put your code up. I'll have to put your code up back up before.
No, but I think you can work with your solution.
Well, the way I did it, I used the object, which was I looped through the array, and in my loop, I had a conditional that says if I'm sorry, excuse me. The object does not have a key at the index of I, then I put that key in there and I put true. And then I keep looping. And if I come across that same key again, I'll just return true. So in this case, we start at 1. One is not in the object, so we push 1 into the object. Then we come across 2. We check to see if 2 is in there. 2 is not in there, so we put 2 in there again. No, we put 2 in there for the first time. And we set the key 2 with the value of true. And when we come to index 2, because arrays are in the 0 index, we check to see if 2 is in the object. And because 2 is already in the object, we return true and we don't move any further because this will be the first duplicate that we come across.
That's correct. Awesome. And what happens if all of them are unique at a high level?
Return false. We finish the loop and return false.
Awesome. Great. Yes. Okay. Cool. And what was the optimization then? From what did it go to, what time complexity did it go to from?
Didn't it go from quadratic to linear time?
Absolutely. 100%. Awesome. Yes. 100%. Now, what about, so that's in time complexity. In space complexity, it actually worsened a little bit, but this is the trade-off that I've talked about a lot, where sometimes you sacrifice space to gain speed, and that's exactly what you're doing here. You're utilizing more space, but you're gaining in time, where you're doing it in linear space. Linear time versus quadratic time. Now, space, what do you think space complexity is?
Oh.
What is the space complexity of the one that I shared? Yeah.
I don't even remember. I think I deleted it.
Which was the nested loops.
Quadratic.
So that's the time complexity, that's right, but the space complexity of that.
I have no idea, to tell you the truth.
Okay. We didn't have any object growing. We didn't have any array growing. So the content on that one, so the space complexity of that was constant.
Right.
Because we didn't have any additional data structure that is growing as we're going. Now here we have an additional data structure, which is that dupes object. That is an object, and that object we're adding keys to it, right? So then the space complexity here, or the space complexity went from being constant
to linear.
To linear. So the in space complexity, this is less efficient, but we prefer time complexity. We prioritize time complexity. We can improve in time complexity. Doesn't matter as much if we have to use more space. Because it's like, I like to make the point that is, in computers you're getting more and more space every time, more memory, more hard drive, but time is limited. We don't have, we only got 24 hours in a day, so better to save on time and use space, because space is being created every 2 years, duplicated or double. I don't remember exactly Moore's law, but that's does that make sense?
Yeah, that makes a lot of sense.
Cool. All right, so so with this new understanding we have, and I don't know, I think Ohidor said he would be right back. With this new understanding, let's try the two sum problem, and we'll see that. Well, let me first share it here. to some. Well, I guess Jonathan, I kind of feel like you're familiar with it already. But with this new sort of refreshing on objects, do you feel a bit more, I guess, empowered to approach this one? Or any thoughts there?
Yeah, no.
What was that? Yes and no?
Yeah, no.
Gotcha. Okay. Let's try it out. Let's try it out for 7 minutes again, and then let's talk about it. I can send the link here. Chat. I'll be right back. Cool. How did it go, Jonathan?
Still working.
Okay. Let's do, should we do 5 more minutes or should we look at it?
5 more minutes.
Sure.
Okay, I really don't get it.
Okay, that's fine. Actually, I was trying to do it for myself again. I discovered I had a flaw in my logic. And yeah, okay. To what point, to what part do you get?
I was trying to see if I could take the target minus where I was currently at and to store that into an object.
Yeah, so actually then I think I misled you initially. So let's take a look at it here. I think I can close this. So yeah, I think this might be what we were trying to do. I realize the importance of trying out our algorithms. So let's take out here. So actually I think we don't want to. Actually, maybe we need to identify this a bit more. So I think I had said let's keep the difference in the object and the index at which we found that difference. But I actually saw an error with that, which is, for example, if the target being 9 for this array, the answer should be 5 and 4. Oh, I think it's message in the chat. Cool. So the answer here will be 5 and 4, right? That's a 9. Or another answer is 2 and 7, actually. But I think the first answer that this is going to find is going to be 5 and 4. But basically, instead what we want to do is let me erase this. Oh, I hate. Why does that happen sometimes? I guess. This. Cool. And let's just draw some lines here. So whenever I have an algorithm and I'm struggling to grasp it, I draw it out like basically like this and telling it out completely. So yeah, what we'll do is we will look at each number. So we need to find two numbers that add up to the target, right? So what we'll do is I'm gonna have an object called complements here that sort of it complements our number. So for example, what number will complement 2 to equal to 9? That will be a 7 will complement that. So yeah, so what we'll do is we're iterating. We start index 0. Element array at index 0 is 2. Oops. The difference, or the which we calculate from the target minus the array sub I, which is 2, will be 7. And we will check if we have 7 in our object of complements, which is what will complement 2 to be equal to 9, right? We don't have it. If we don't have it, we add this number. We add that number and its index. So we add 2 and 0 as the index. I think, Jonathan, I think I had said we added the difference, but I was drawing it as you were doing it. I was also doing it with the difference, and then I discovered that that didn't work in this case. Do you have any comments on that? I apologize.
Kind of get it now.
And basically, so we added the number, we added the current number there because we want to check it. We're gonna be able to check it faster, and that's the point of the object. Then after that, we move on. So now I is 1. The array at index 1 is 5. What number will complement 5 to be 9? A 4 will nicely complement a 5 to be 9. That's the difference. We check if we have the difference. We check if the difference is in the complements object. It is not. If it's not, we just add the current number we're on, which is 5, and its index. We keep going. We move on to 2. Array is up. 2 is 3. A number that will the difference will be target 9 minus 3. That is 7. 6. We check if 6 is in our object. Have we seen a 6 so that we can complement this 3? We haven't seen a 6. We have seen a 2 and a 5. Then we just add the current number with its index as the value. Then we move on to the next one, which is index 3. The current element is 4. The difference is 9 minus 4, 5. And here, have we seen a 5 in our complements? Bingo, we have a 5 in our complements. A 5 will complement a 4 to be equal to 9. We have that in our object. We saw it here. Therefore, we can, if the difference is in, now we know if we could do diff, if diff in my ends are in complements, then we can return an array with complements at array, complements at diff. No. What am I saying? Yeah, complements at diff. The difference will be the 5 with just I. Does this make sense?
Yeah, it makes sense.
Cool. Okay, now let's implement that, Jonathan. And Hidora, I know you had stepped away for a second, but this is one of the problems that that I want you to work on for the hash tables reassessment on DSA. It's called two-sum. I shared it in the chat, and we're basically described here how to solve it. The key is we need to find 2 numbers in the array that give that add up to a specified target, and we need to return the indices at which those 2 numbers are found. And in this case, the indexes at which 2 numbers are found that add up to the target is 5 and 4, or index 1 and index 3. And the way in which we did that is we just sort of walk through. We calculate the difference of the target and the current number. The difference from 9 minus 2 is 7. We check if we have 7, if we have seen 7 in our object. If we have, we just return. In this case, we haven't, so we just add 2 to our object or current element with its index as the value. And we just keep doing that until we get to 3, at index 3, where we see that the current element is 4, and we calculate the difference between the target and the current element, which will be 5. And we basically ask, have we seen a 5 in this object that I decided to call complements? We have, in which case we then found the 2 numbers that add up to 9, that is 5, and this 4 we had seen, this 5, which we saw here, and this 4. And then the index will be 1 and 3. any questions or thoughts? Cool. Jonathan, let me know if you have any questions as well, or once you have it.
Got it.
Cool. All right. I see your message over here. I'll make sure to upload this recording as well.
Awesome. Thank you. Sorry about that, Leo.
No worries. Take care.
Okay, Leo, I think I got it.
Cool. Do you want to share your screen?
There we go. So I created the object and then I looped through the array, and I was checking to see if the key was already in there. And if it wasn't in there, then I put the difference, which was the target, minus whatever the different whatever the value was.
Right.
At
The
key.
current number. Mm-hmm.
So when the target is 5, and 5 minus 1 is 4, right?
Mm-hmm.
And since we don't already have a 4 in there, we keep going. So the next one was 5 minus 2, and the difference was 3.
Okay.
And then I set 3 with the value of 1. And then because the next one was 3, 3 is already in there, right? And the number before 3 was 2, so 2 and 3 is equal to the target.
Yeah, but the way you explain it there, let's try again, because I feel like that part where you said like the number that was before the 3. So we're in 2. Let's do. We're in 2. What happens when we're in 2?
We don't have 2 in the object, so
Okay.
I put the difference of 5 minus 2 equals 3. So 3 was the key, and I set the value of the index to 1, because 1 is where
Yep.
1 is where I is at. So if we was to look at array at nums at index I, and which was the current value of 1, we would get 2.
Correct.
So we move on to the next index, which is 3, and 3 is already in there. So only thing I did was I returned
Mm.
uh, I returned the object at I, and I returned the index as well. So it was, I returned the key of 3 and the current index of where I was at now. Because since 3 was already in there, the difference of 5 minus 2 is 3, and I use that as a key. And since the key was already in the object, I found my target. So I just returned the key of 3.
Wait, I'm not
I know
sure
how to
then.
explain it.
But I feel like also, something that makes it complicated is also that this is where you could use some variables to aid.
Mhm.
So for example, you have a lot of like nested square brackets, which is sometimes just hard to look at for our eyes. So for example, this is an occasion where I'll say, I don't know, maybe in line 149 or before 149, I'll create another variable, maybe call num or current num. That is equal to, CRR, it's fine, nums at I, and then I will use that instead of having to,
I'm sorry, I was leaning back. All right.
Wait, you wouldn't need to then say nums, just current.
Oh.
Yeah, object at current. Cool. And what else? What do you return if the pair is not found?
Oh. There we go.
I actually think it might be -1. I don't remember. Let me see. The problem. Is it false or? Oh no, it says that you're gonna have exactly one solution. So in fact, you don't need to return anything then if it is not found. Okay, but so actually, so this is, you're putting the difference in the object. So this has one slight problem, which is the problem that I discovered. Flip 2 and 3 in the array.
Oh.
Oh well, that looks like a syntax error. Okay, let's see. Let's try it again.
Still there.
Oh, it works. Wait, hold on, because my brain is spinning right now. Let's see. You have the current. Let's try with the example that I had. Should still work. I'm gonna copy it here. 2, 5, 3, 4, 7, 10. Try it with that one that I just sent in the chat.
Okay, let's see if this works.
And let's say the target is 9.
1 and 3.
1 and 3, that's correct. Okay, let me just try to see to understand this for myself, kids. I thought this was what I was doing before, and then I discovered a bug, but then maybe, yeah, I'm still confused. So you check it if the current number is in the object. Then you know you can return the current number and the current index. Otherwise, you add the difference to the object. So let me draw here. Actually, I guess. Let me move my pen to this monitor. Cool. And then, okay. So I'm trying to see what the object is going to look like, which is this. Oh, well, I guess you have a console log as well. 4, we see 7 being added first because 7 will be the complement, and then we do 0. And then after that, we see 4 being added because the 5 will need a 4. And then after that, we see 6 being added. Oh, I'm sorry, I think it was, this 4 was a 1. And then we see, and then when we go to 4, yeah, how is this working? Because when we go to 4, oh, yeah, I see. When we go to 4, we check if 4 is already in our object. It is. Then we just return the current one, which is 3, and object add current, which is going to be 1. And we see 1 and 3. Great. Yeah, this works.
I'm trying to
I
think
think
I got 2 6s though.
you got 2 what?
2 6s.
No, but you didn't get 2 6s. You get 6 is at index 2.
Yeah, 6 at index 2.
Or you need a 6 with the number at index 2, which is 3. You need a 6. That's what this is saying.
Yeah.
Right? Yeah.
See it now.
So I kind of feel like I'm just looking at 2 sides of the same coin, and I'm not recognizing the coin as a whole. But this is, yeah, this works exactly the same as I was describing as them. But I was thinking, like, what if the way that I was envisioning it was, what if we actually, yeah, is 2 sides of the same coin? Because what I was suggesting here is if the object has the difference inside. Oh, but this is horrible. My handwriting is so bad. If the object has the difference, this is the way that I was seeing it, which is this other side of the same coin. Then in here, I wouldn't add the difference, I would add the current. But those two are the same thing. Oh, actually, not if. I'll just say object at current equal I. But these 2 things are exactly the same thing. As long as, yeah, I don't know if you see that.
I do see it.
Yeah, it's the opposite of what you have, which is then the same at the same time. Is that, I guess, like, you're checking if the current is here and adding the difference. I am checking if the difference is here and adding the current, which ends up being the same thing. Cool. Okay, does this make sense? Sorry, what was that?
Do I get credit for this now?
You get credit for this, yes. Yes, this counts. This counts. Make sure to push it. And what was the other one?
I got a couple of them to do. My brain is
I think there's just two more, but yeah, you do those whenever you get a chance, I think. I think, do you have our notes? Yeah.
Somewhere. I gotta go through my Google again.
Yeah, I can send it here, but yeah, I'll recommend you bookmark it. But yeah, it's a unique number of occurrences and keyword words. But yeah, if possible, try to do it tomorrow because you have objects fresh right now.
Yeah.
And it's gonna help. Cool. All right, Jonathan, I think that's it, man.
Yeah, thank you.
Of course. You're welcome. I hope you have a good night.
You too, Leo.
Oh, you're coming tomorrow for the demo to see your peers?
Yeah, I'll come tomorrow.
6:30. Cool.
Got it. I'll be there.
All right. I'll see you tomorrow. Take
Later,
care.
Leo.